Hi, welcome back. In this lecture I want to talk about a notation to represent qubit or multi-qubit system, and it's called a circular because we're going to use a number of circles to represent each state. So each state will be characterized by a phase and an amplitude, and we're going to use this circle notation. This is particularly useful notation for debugging purposes and to deeply understanding the quantum computing algorithms. So we're going to use extensively in this module and in the next modules. So we can represent the classical bit using the circular notation. So conventional bit can have only binary values, so it can be either 0 or 1. So we're going to use two circles. So one circle for the state 0 and one circle for the state 1. So if we fill the state 0 means that the system is in the state 0, and if we fill the state 1, so if we fill the circle means that the system in state 1. So this is very simple, right? You might ask yourself why we use the circle. Well, the answer is in the next slide. The reason that is that we want to use we want to use circle notation to represent superposition in the quantum system. This also means that there is a certain probability to find the system in the state 0 and certain probability to find the system in the state 1 after the measurement. So we want to represent this probability by using the area of the field circle. So here, this area is larger than this one. That means that also the probability of finding the system after the measurement in state 0 is larger than the probability of finding the system in the state 1. So these two amplitudes here, they're going to be reflecting in the area. Also, we are going to use another line here to represent the phase. So there are two major parameters to characterize the circle notation. One is the magnitude and the amplitude that is related to the radius and the area of this circle. So in this case you see both circles have the same area, so it means that they have the same amplitude. That also means they have the same probability of measuring state 0 or 1 after the measurement. The other point is the relative phase, that is the rotation of the state 1 with respect to the state 0. So what is the relative phase? In this case is relative phase of state 1, so we take this line here with respect to state 0 phase. So in this case the phase is going to be 180. Let's look at some example using the circle notation for one qubit system. So we're going to have two circles, one for 0 and one for one state, and then let's see at different cases. So in this case, this is basically a classical system, but we do have a phase here. So the probability of finding the state 1 is 0 because this is completely empty. The opposite case is this case here, where the state 1 is completely filled. So the probability of finding a system in the state 1 is going to be 100%. And when you have these two examples that are very similar, you see that the area for these two cases is all the same. That means the probability of finding in state 0 or 1 is the same. The major difference between these two systems is the relative phase. In this particular case, we have 180 degrees. So just to summarize, the square of the magnitude associated with the 0 and 1 state determines the probability of obtaining the value without measurement. And we know this from previous lecture. The radius represents the magnitude. So the shaded area in each circle is directly proportional to the probability of obtaining the circle value 0 or 1 after the measurement. We are also going to use the relative phase. Right, so we use the relative phase of state 1 with respect to 0. And you can see that we can take only values between 0 and 360. As I said, we are going to use the relative phase and not the absolute phase. And why is that? Well, because what really matters is really the relative phase between two states. So as you can see here, these two systems are actually equivalent because they have the same amplitude and then the same relative phase. So what is really important is just the relative rotation between our circle of interest. One important point for this course is that we're going to apply a rotation operation on the qubit with the quantum gates. We'll see in the next few lectures. So if there is a Q operation that basically rotate the qubit, this also can be equivalently considered as an effect of only on the one circle. So since it is a relative phase and these two states are equivalent, whenever we do a rotation on a qubit, what we're going to do is just to apply rotation on the state 1. So that's important for relative phase, and that's something that we're going to see in the next few lectures when we're going to talk about the rotation gates. So what is the impact of relative phase on a measurement? Well, the impact is actually zero, so the relative phase has no impact on the results of the measurement. What it really matters is actually the area of our circle. So why then we want to have the relative phase information? Well, it turns out that we are going to use the phase to encode some particular values in the qubits. And then we're going to see some very smart algorithm to express and to transform the difference in phases in difference in magnitude. Once we have difference in magnitude in the qubit, we can also measure it. So we will see many interesting algorithms how to take advantage also of the phase. But in this particularly simple case, if I give you two, like a qubit system, and then I tell you and ask you what is the impact of the relative phase on measurement, the answer is nothing, because what really matters is actually the area of the field circle. It turns out that frameworks like QCKit or Cirq do not provide output of the qubit state in the circular notation, but obviously we can actually implement those. The only things that actually we need is an expression of our qubit system as a vector, as a normalized vector, where we have each element of the array is going to be a complex number. So C0, C1. So it turns out that there are some function from both QCKit and Cirq to get the values of this vector. Once we have this vector, we can implement ourselves the function to plot the circle notation. As an example here is a code that I wrote using Python and then matplotlib modules from Python. But basically, what I get this the qubit, the state, and then I calculated what is the amplitude and then what is the phase, and then I provide these two values to the routine for plotting. So do not worry about this. I'm going to post this on Canvas, so you can follow with a little bit more time. Obviously, then you can just simply call this visualization routine, and then the results will be something like this. This is the last slides, and talk to you soon.